Okay, so we will start with a brief review of the techniques we have learned in this chapter. The first one we learned is this integration by part. It comes from this product rule. When we take the derivative, the integration by part, if our integral can be organized the following form. This integral is kind of equivalent to this integral up to a sign and a given function. So sometimes we want to find a simpler one to find the integral of this complicated one. And for the definite integral from A to B, will be the values at the two endpoints of same integral. Okay. As the application to this, we integrate the following. And we can go further, even this. This one has just one function, but we don't know how to find the integral directly. What we do is we make a 1 over there, make this look like what we had over there. We find what f is, what g is, the derivative, and the g. We use this to find the integral. Similarly, we can find x logarithm x dx. Okay. So in this case, there's something new about this. Let's try the following. With cosine. Okay, another practice of this integration by part. E to the x cosine x. Okay, Sakina, which direction should we go? What's f? What's the g derivative? Okay, let's try that. We're going to set f g derivative f x gx f derivative gx dx. In this setting, f is e to the x. G derivative is cosine x with g. Sine, okay. Now we find the derivative. G is sine. Okay. Sophia, let's compare these two integrals, this one and this one. Do we get something simpler? Do we get something similar?
Something similar.
It's very similar. You can see, so this integration by parts does not give us something simpler. What should we go? Okay. This time we have choices. We choose to go ahead. with the same process. So it's very important that we go the same direction. So this will be our f. This will be the new g derivative. We go the same direction. We want to apply the integration by parts again. I copy the function. Again, I will use this formula, fx gx derivative gx dx. Okay, copy this part, see the same. Okay, Sophia, now what is f?
F is
Easy, oh,
yeah.
e to the x, okay. What is g? Derivative is sine.
Negative cosine x.
Negative cosine x minus f derivative still is x. G is negative cosine with plus. Okay, now let's drop the parentheses. Okay, Sakina, let's drop the parentheses. What do we get? Okay, it's cosine x. Now let's see what we have arrived compared with where we have started. Is this simpler? It's exactly the same. Okay, so the same thing happens. We wanted to find the integral. We didn't succeed in that, but we did get something interesting. We get an equation about this term. So how do you find this unknown term? Elisa, what would you do?
Add the integral to both sides and then divide both sides by 2.
Okay, so we have this. We have it again here. We will group these two together. We have twice. Okay, so instead of finding the integral by integration by parts directly, we end up with an equation. It's not a done, but it's good enough. It's good enough in the sense that we can find this. We divide by 2, this gives us the integral. So this is another application of this integration by parts. Integration by parts. Then in the second section, we learned this trigonometric. The key idea behind these integrations, cosine mx nth power tangent m's power secant nth power. The idea behind this is we want to convert them to polynomials. If we succeed in that, if we can convert this to polynomials, then we know how to integrate the polynomial. That's very easy. So we find the proper substitution. So for the first one, if one of the powers is odd, 3, 5, 7, we split one, let's give it a substitution. Okay. If n is odd, if both are even, we use trig identities. All of them are even. Double angle formula. Second case, similar. If this sixth power is even, again, we convert everything to polynomial. If m is odd, then it's good. Okay. The remaining case, trig identity. Okay, that's the second section about the trig integrals. So the main line is converted to a polynomial, and we know how to integrate a polynomial. That's what we are good at it. Okay, so with this, we can integrate the trig functions. In some case, we need to first convert the integral to trig functions. So we go more broad and more general and more complicated integrals. Okay. So in this section, we deal with three special factors. If we have the following, whenever we do integral, the square root of something is very complex. It's difficult to integrate. We try to get rid of this square root as soon as possible. So if it's the difference of two squares with x squared minus x squared, then we use substitution. In this case, x from negative a, it's a new range about theta. then this factor. Okay. Now, if our integral has this factor after this substitution, we will get a trig integral. Then we use what we have learned in section 7.2. Trig integral in second case, if I have the following square root factor, two summation of two squares. Okay, second, what substitution would you use? Want to get rid of the square root. Yeah, theta, okay. So what's behind this are the trig identities behind the substitution. For the first one, the trig identity we have is cosine square. For this one, the trig identity we have is the range of the square root. Again, in the end, after substitution, we get a trig integral, and we can integrate using the method in the previous section. The third case, x squared minus x squared. Elisa, what substitution do we use for this one? So what's the trig identity behind this substitution? Okay, maybe Sophia, you want to try? What's the answer to this, Sophia?
Is it a
Oh, let me correct myself. So here it should be the secant square. Okay. So for this one, we will use the same identity, but in a different appearance. There will be secant square minus 1 is tangent square. So now we use the substitution. This time we consider the domain when x is bigger than equal to a, the theta. Then the square root. Oops, wrong direction. Okay, so this substitutions, the only purpose is to get rid of the square root, square root, square root, square root. Whenever we can get rid of the square root, we consider this a win for the integral. Okay. Then in the next section, we learn a new method, partial fractions. It is something we have just briefly mentioned last time. Let's review what we have done last time. 1 minus u squared. That's what we had last time. On the denominator, we can write it as the product. 1 minus u, 1 plus u. Okay. The partial fraction decomposition allow us to decompose this into something simpler. A, B. Okay. We have more terms, but each term is simpler. So previously, on the denominator, it's a quadratic term. After this decomposition, we only have linear term, and we know how to integrate them easily. To find A and B, the method will multiply both sides by the two products. We get this will be A plus B, A minus B. We'll compare the coefficients of the two polynomials on the left side and on the right side. This side, there's no linear term, so A minus B is 0. From here, we solve A and B. We have the decomposition, so we can complete the integral. Okay. Then next, we move to the general case. So the general case, the first, we introduced a term called proper rational function. If the degree of the denominator is bigger than the degree of the numerator. If it's not proper, we use long division for polynomials reduced to the integral of a proper rational function. Okay. Then we will recall a theorem. Maybe you have seen some form of it before. The fundamental theorem of arithmetic. Okay, let me check. Who had seen these terms before? Fundamental theorem of arithmetic. Have you, Sakina? No? Sophia, have you seen this before?
No.
And Elisa?
No. Okay, so this, I think you have seen the theorem, but don't know this name. It says something, any positive integer bigger than 2 has the decomposition. here P, these are prime numbers. And EJ bigger than equal to 1, power. Okay, I'm sure you have seen this. Sophia, you have, right? This decomposition of integers.
Yeah. Oh,
It's
yeah,
very
yeah.
easy.
Yeah.
It's very easy. It has a very big name. The name is very big. Maybe you just don't know the name of this decomposition. It's called the Fundamental Theorem of Arithmetics. Why do we have this? Because we have a system of fundamental theorems. In this course, we just learned one, fundamental theorem of calculus. Okay, Elisa, what's that? Elisa?
They're inverse of each other.
Uh-huh. Okay, so yes. Fundamental theorem of calculus means the integral and the derivative, they are opposite to each other. We have another fundamental theorem. So in the future, you will learn quite a few fundamental theorem of line integral, fundamental theorem of this or that, but today we have a similar one, fundamental theorem of algebra.
I think I remember that one.
Okay, what I say?
It's like every function has the number of complex roots as the leading term's exponent.
Okay. Yes, so let fx be a polynomial with complex coefficients of degree n. Then we have the decomposition. It can be written as the product of so here these are the roots counted with multiplicity. And the EJ is the multiplicity. Oh, I forgot this coefficient A over there, correct? This is about the fundamental theorem of algebra. Any polynomial can be decomposed into the product of these linear factors. If there's multiple repeated root, then we have this multiple. If no repeated root, this will be one. We have a simple product. Now we'll give us another version of this. If we start with real coefficient, we want real factors. Okay, so the real version, the real number version. let fx is the real coefficients of degree n. Okay, here another is the summation of the multiplicity 1 to k is okay. Real coefficients, we have a similar decomposition. Okay, you can see the difference between the two decompositions. If we allow complex roots, then all of them are first order, just the difference. But if we only allow real coefficients, real solutions, it's possible we have some quadratic factors. This factor has no real root. The discriminant. Okay. So in the same way, the degree and summation of the linear term and twice of summation of the quadratic term. Okay, I will check with you about this decomposition. Any questions? Sakina, no. And Elisa? Okay, and Sophia?
No.
Okay, so it's similar to this fundamental theorem of algebra. But if we only allow real coefficients, only allow real roots, then we have to admit this quadratic term. In this case, we say this is irreducible. Okay. In the following, we will use this fundamental theorem of algebra to do this integration by partial fraction decomposition. We start with simple cases, and step by step, we go to the more general case. Partial fraction decomposition. Okay, the first case. We assume it's a proper degree p less than degree q. The first case when q first case is the simplest case. There's no repeated root and no irreducible factors. No repeated. No quadratic factors. in this case, the polynomial, the rational function, can be written as okay. So if we can find this coefficient, a1, a2, up to ak, the integral of this complicated rational function can be done through k very simple integrals. We can do this very quickly. Okay, let's see an example. So the point integral. Okay, let's do something. Let's skip this. Our first example, let's try 5. Okay, first let's check this factor. Is it, can we factorize it? Sakina, x squared minus 3x plus 2. It's x squared. Nice. Okay, Sophia, let's set up the partial fraction decomposition. What's this?
It's
How to set it up?
a over x plus 1.
Minus 1.
Oh, x minus 1, and then plus b over x minus 2.
Okay, so we have set up the partial fraction decomposition. Very simple. Okay, Elisa, what should we do next? Yes. I haven't heard anything, Elisa. Maybe you can keep yourself unmuted, so you don't have to mute, unmute. You can say Sophia, she's unmuted all the time. It's okay.
You rewrite it as a times x minus 2 plus b times x minus 1 over x minus 1 times x minus 2.
Okay, so it's the same as we get rid of the denominator, we get something much simpler. Okay, so 5 is a plus b. X, oh, my x is bad. Plus minus 2a minus b. Okay, we compare the coefficients. There's no x on this side, so the coefficient must be 0. Coefficient, this is 5. So minus 2a b is 5. We'll solve a and b from this equation. So, okay, Sophia, how do we proceed to find a and b?
You can add them.
If we add the two equations, we get a plus 0, -5, negative a is 5. Oh, I'm sorry, add, not subtract. Get distracted. It's 5. Negative a is 5. And that's b equals negative a. Okay. So we have the decomposition. A is -5. B is 5. Then the integral. Okay, let me give you a few minutes to find this integral of the quadratic function, rational function. Squared 3x. Okay, let me know when you finish. Let's start the work. Okay, so we have the decomposition. So the first step, you replace this factor by the decomposition. Then the integral of the two parts will be the integral of them separately. Okay, so the first step, just the substitution. So it will be -5 dx. I'm sorry. I copied everything. Okay, the integral of the addition is the addition of the integrals. And we can pull out the coefficients, -5, +5. Okay, Sophia, what's the first one?
ln
Uh-huh.
x minus 1.
Again, don't forget the absolute value. 5. And Elisa, the second one.
ln absolute value of x minus 2.
Okay, now the integration constant. And we have the rule for this logarithm, so we can simplify this a little bit. The difference will be the quotient. Okay. That's how we integrate this rational function. We use the partial fraction decomposition to reduce it to much simpler ones. Okay, let's make it a little bit more complicated. Example 2. Fx equals, okay, let's make it an integral. Let's find this integral. 5. Okay, so let's have 5 minutes break, and we'll work on this problem after the break. Think about where do we start? Okay, 5 minutes break. Be back at 51. Okay, Sophia, what's the first step? Where do we start?
You factor it.
Okay, the denominator, x cubed 3x squared plus 2x. Okay, what's the first obvious factor?
X.
Okay, so we have a common term x. We can factor this out. Then it's what we had in the previous one. So we know this factorization. Then we set up this partial fraction decomposition. Oh, not this, not needed. Okay. Lisa, what's the next step we should do?
5 equals a times x minus 1 times x minus 2 plus b times x minus 2 plus c times x minus 1.
Okay, so we get rid of the denominator, we multiply both sides by this. This goes to 5. A over x multiply this, we cancel x, copy the rest. Okay, how do we find the coefficients? What method would you use, Sophia? A, B, C.
There are no x's, so it has to be 0.
Okay. So one method is we find the x squared term, x term as constant, we compare with the left-hand side. Another method in this special case is this equation is true for any x. So we can pick a few special values to help us find this ABC. The first special value is I'm going to pick that Q's these two terms. If I set x to be 0, because it's true for any x, in particular, I can pick 0. If x is 0, this goes away, only this term left. Okay. So a different method in this special case. Fine. A, B is 0, C is 0. Again, the logic behind this is we want this to be true for any x. But what we have, we can, since for any x, we pick a special one. X is 0, this term goes away, this goes to 2, so we can find A relatively easily. Okay. Elisa, what other values would you pick to Q some extra terms?
X equals to 1.
Because 1, so the left is the same, but the right side, because 1, this is 0. Next to 1, negative 1, next to 1, this is 0. So we find B. Sakina, give me a third value. 2 equals to 2 to 5. Again, this is 0. 2, this is 0. C, this will be 2, 1. Okay, so in this special case, we have a simpler method. We don't have to reorganize, collect, solve the system of equations. We can pick a few values. So we pick these values as special as possible. Each time we kill all of them except one. We found this one, a different value, kill this two, we found this one. Okay, now we have the decomposition. A is 2 over 5. Just like over x. B, negative 5. C, 5 over 2, x minus 2. Then let's finish the integral. Okay, I will give a few minutes to finish this integral. Rather complicated function. But using this partial fraction decomposition, we decompose it to the 3 simpler ones. So we can integrate them relatively easily. You finished? Okay, how do we continue from here? Okay. 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 So 2, 5, 5, oops, x minus 1. So this will be okay. So that's the first case when there is no repeated factor and no quadratic factor. We have the decomposition, and we can decompose this to very simple ones that can be integrated easily. Okay. The second case we allow some repeated factors, but no quadratic ones yet. Starting more general. That's Q, should be fx. Ah, yes, it's qx. It's qx. Okay. Then each factor will give us a few extra terms. Let's see an example how we set up the decomposition. Okay, this time we have repeated factors, square and cube. But of repeated factors, so this will give us two summation terms. This give us three summation terms. Let's see what they are. So if we have a repeated factor, this will give us two terms, one for this, one for that. A cubic factor gives three terms. Okay, Sophia, if we have x to the fifth, how many terms do we have?
5.
Okay, so it will be x minus 5 and minus 5 square of x minus 5 to the fifth power. Okay, then to integrate this, we should recall the integrals. This one we have done it before because logarithm. What about the square? Elisa, what's this integral? You are muted. Are you seeing something? Okay, yeah, still muted. So I'm going to write down the solution. It will be negative. Similar, if we go to the higher power, maybe Sakina. So we integrate this 1 over this cube. So something whose derivative is this. Okay, so this is something, so it's x minus a negative 3. So x minus a, this power minus 1 go negative 3, negative 2. Okay, that's the first step. We do this step by step. If we only have this, when we take a derivative, this goes negative 3, but we will have a constant or negative 2 over there. We have to kill this factor. How do we kill this one? Yes. So that negative 1/2. Then we can check if we take a derivative, we do have this. That's how we find the integral, find the antiderivative. Okay, so if we can integrate all of this, then by this partial fraction decomposition, we can integrate all of this. Okay. Okay, let's try to find the coefficients. So the first step, we are going to multiply both sides by this factor to kill the denominators. Kill the denominators. A A2. B1. B3. Okay, there are many coefficients. We find them one by one. We will apply the same trick. This is true for any x. We check a few special x's. Okay. Go to 1. So 1 equals A1, 0, A2. That's 1, 0, 0, 0. So check the value at 1, we get negative A2. So A2 is negative 1. Second one equals 2. 1 equals 0 of 2, 0 equals 2. 2, so it's B3. B3, 1 squared, B3. Okay, so we found 2 terms. How do we find the rest of this? A1, B1, and B2. We already used the 2 values. Okay, what we do is we plug in what we have found, A2 and B3. Try to simplify and use this to find the remaining coefficients. So plug in 1 equals A2, so A1, copy A1. A2 negative 1. We simplify this. This is this is okay. We put these 2 terms to the right hand side. So we have A1, B1 equals to 1 plus this gives us x cubed minus square plus 2x plus 10. Oh, subtract. That's incorrect. Subtract. Subtract this. Subtract square. So this will be x cubed minus 3x squared plus 6x is 8. Because 1. One minus 1 cancel each other. 8. X equals 1 minus 3 plus 6 plus 8. So the sign is incorrect. Let me check what happened. X minus 1, x minus 2. Q. Okay, so here I made mistake. When you apply this cubic power, the formula should be A minus B cubed, A cubed, 3A squared B, 3A B squared B cubed, minus B cubed. So there are some factors. That's why I don't get I wanted. So here should be times 3 times 3. So now give us 6, 12. If the 6, 12, so it will be 7. 7, 14. 14 now it'll be 7, 14. Because this gives this 0. Okay. Make some corrections. Okay, so the next, we wanted to simplify this equation. This equation now, if we check, they have a common factors. X minus 1, x minus 2, x minus 1, x minus 2, x minus 1, x minus 2. They all have x minus 1, x minus 2. So we have this common factor. X minus 1, x minus 2. A, what's left? Minus 2 squared. B1, x minus 1, speed 2, x minus, okay, x minus 1, x minus 2. Then this side should also have this factor. So we will use long division to factorize this polynomial. X cubed 7x squared 14x minus 8 divide x minus 1 squared negative 6x squared 14x 14 negative 6x, so negative 6x squared plus 6x 8x plus 8, so plus 8. Okay, so we have one factorization. Second factorization, x minus 2. X minus 4. Okay, so with this preparation, we have the decomposition. X minus 1, x minus 2, x minus 4. Now we can compare this but after we eliminate the common factor. The common factor, we get something much simpler. A1. Okay, so we can apply the same trick. Now a new round of the trick. So x equals 1, x equals 2. Because 1, so this will be a1 negative 1 square. Equals 1, this a 0, a1 equals 1 minus 4 negative 3. So a1 is negative 3. Equals 2, 0, 0, b2, 1, 2 minus 4 negative 2. Okay, so for the three of them, A1, B1, B2, using these substitutions, we found 2 of them. Now we have 1 left, B1. Okay, to find the B1, we can check this identity. On the left, there's no square term. On the right, this gives us A1 x squared, this gives us B1 x squared. So A1 plus B1 must be 0. A1 plus must be 0. B1 is negative A1 equals 3. Okay, a little bit work. We found all the coefficients. Okay, let's give a summary. So it's 1 over So B1 is 3, A1 -3, B2 -4. So this -1 and 1. -1 and 1. Then the integral of this very complicated rational function is reduced to 5 simpler integrals. We can integrate them. So this one without much difficulty. Let me finish this. -3. The first one's easy, logarithm, as we have done many times. Second one is minus will be plus. Third one, logarithm. Fourth one, again, plus. This one will be half. And with constant. Okay, so this is not an easy example. We spent a lot of time, and I made mistakes in the process. Through this process, you can you see how we integrate a rational function when there are repeated roots. And wait for this to synchronize. So if there are repeated roots, we set this up with this from the linear first order, second order, first, second, third, to how many orders we have, how many terms we need. We find all the coefficients. Sometimes it's not that easy. We can see this here, have to do this several steps. The first round give us 2 of the coefficients. Second round, another 2 coefficients. Then third round, we find the last one. Then so the integral now becomes easy. The difficult part is to find the coefficients. But that is some algebra. We can do that without much difficulty. Just some more patient, be careful. Okay, we stop here. Okay. Any question from the 2 of you?
No.
All right, okay. Okay, see you on Wednesday.